Here comes the space station right up there. Right behind you. Okay. We're going to do a countdown before it disappears because we have to wave to the people in the space station. Alright? Can everybody see it alright? Okay, so we have to count down from, what do we count down from? 10. Okay, start from 10, we'll go down to 9. Okay, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay, we have to wave.
Bye! Hi!
I always wave to the people.
There it is, I can see it in my viewfinder now.
Maybe they're looking down at us.
Yeah, see?
Look how bright it is. Because now we're going to see a picture of that space station in a couple minutes. It has huge solar panels. Why do you put solar panels on the spacecraft? To get energy from the sun and turn it into electricity. That's right.
I already know that. Isn't that like a packet?
Look at this. It's coming right over us. Just special for us tonight.
There it is.
And guess how far away they are? Know
Yeah.
how far up they are? They're 400 kilometers away from us. It doesn't look that far.
I'm not sure.
400 kilometers. That means you could drive from here to Montreal and back. That's how far up it is.
Or from here to Toronto.
Yeah, or from here to Toronto.
Bye-bye.
Yeah, it's going into your shadow now.
Pretty soon.
Boy.
Oh, look, it's
Boy.
going to disappear into your shadow.
I can see it. It's almost disappeared. Still there. It looks like a star.
Who can still see it?
I can.
Yes, I can just see a dot.
Okie doke. Good evening, everyone, and welcome to the March 2010 meeting of the Ottawa Centre of the Royal Astronomical Society. We have a fairly full program for you tonight. I hope you're going to enjoy it. Chris, could you flip over to the agenda? There we go. Not necessarily in the order we're going to present it, but nevertheless, we have Tim Cole doing Ottawa Skies, talk from Richard Alexandrovich. Al Scott will be doing the astronomy news update. Eric Kujala will be speaking a bit about some M31 images. We have observations, we have lunar and deep sky challenges, and our favorite presenter, Simon Hammer, will be presenting some images from the Japanese Selene mission to the moon. So some very, very high quality lunar images going on tonight. Next slide, please, Chris. Okay, so we'll start off with Tim Cole, who I just sent to the back of the room, so we'll have to run back down here again.
Oh no, not this newfangled thing. So yeah, we've got guess what, it's March, and here's our nice set of seasonal constellations. We're coming up, next month will be really nice, but we're coming up on Leo. And we now have two nicely placed planets for your viewing enjoyment, and Saturn is even up at a sensible hour, so you have no excuses to stay up all night, unfortunately, but there you have it. Planets. Yes, Mercury visible shortly after sunset, but you'll have to wait for a little bit yet. But Venus is really nice. I noticed it glaring in my eyes as I was heading out the door coming here this evening, so Venus is all nice. Mars, well, Rolf is going to show you some good stuff with that, but grab it while you can. Sorry, folks, Jupiter's dead for a while. And Saturn, oh man, it's getting nice. So anyway, we've got some fun stuff for the planets. Always good stuff, particularly for newbies. And even for the oldies, or whatever we are anyway. So lots of good stuff for planets. We have a nice thin crescent moon coming up mid-month. This is a one-day-old moon. And they're kind of, I find them tough to see. Maybe you guys find it easy, but I find it tough. So for me, I find it kind of nice to find the thin ones if you've got something nice and big and bright for a signpost. So we've got Venus up nice and close to it. So you might have a crack at finding a really, really thin moon. I have trouble with them. My eyesight stinks, so maybe you'll have better luck with it, but we'll find out. Moon Occulting Pleiades, we've done a few of these, but this is 2055. Oh yes, sorry, I realized I put the time in. Never mind, shut up, Tim. This is actually the last occultation until something like 2023. The last lunar occultation visible from North America of the Pleiades until 2023. So, here's a nice opportunity to get it. Do I have to do anything to get this animated? Chris, do I have to do anything to make this do something?
Ask me.
Oh, Chris, could you make this do something? Yes, there we go. There's a fun little, I always like these ones, particularly the Pleiades. I really like them better when it's the opposite phase, because then you've got the stars popping out of nothingness, which is kind of fun, but this is fun too. So this isn't that unusual, or hasn't been up to now, but since it's the last one for a while, enjoy it while you can. I threw in a couple of binocular clusters. I find it kind of fun to go find stuff in binoculars, and the nice part with binoculars is if you can find it in binoculars, you know you're going to be able to find them in a small scope. So we've got the classic one, there's M44, the beehive. And this one's not quite so classic. It's M67. It's a bit of a faint one, so it's going to be a bit of a stretch for binoculars. But M67 is kind of a nice one, simply because it's unusual. It's one of the oldest open clusters that we know of, and it's about 4 billion years old, which compared to a globular is pretty minimal, but for an open, it's a nice significant age. A little tricky, or at least for me. I'm sure you guys will do better than I would, but fun, enjoyable. And then there's M44, really nice in a pair of 10 by 50s, at least I find, and a rich field is really nice. And for a little more challenge, M81 and M82, which I've found in a pair of 11 by 70s out in, 15 by 70s, sorry, it's 11 by 70s here, 15 by 70s in reasonably dark skies, but I haven't had much luck from my backyard. So there we go. I'll see what I can do this time. This is a nice little 4-inch refractor, and this works even at my crummy light polluted Nepean yard, so you should have reasonable luck with it. They're fun little galaxies. So there's some good fun with them. So all told, it's a fairly, oops, sorry about that. Richard stole from your parade. So other than that, it's a fairly mild month, but it's a fun one, and go out and enjoy some skies and hope like heck that we have some nice ones. Okay, I'll pass this on to the slim and svelte Bill.
Why, thank you. Next up, Richard Alexandrovich to speak to you about some interesting celestial bodies.
Good evening, everybody. Nice weather out there. Anyone who says it's not because of global warming, well, I think better think twice. Talking about gravitationally challenging, I'll be talking about an object that deals a lot with gravity. I think everybody will have a problem with gravity with this one here. We're into the field of stellar evolution, and we'll be talking about something toward the end of the star's life. In fact, it's a resurrection of like just as the title says, a beast of another nature, something completely exotic and very different. I find it interesting as well. Like I said, it's the final chapter in a star's life, but not any star's life. It's a star with a very massive star, more than 5 times the sun's mass. Stars with about 8 solar masses or more will become a white dwarf. Those that are greater than 20 to 30 solar masses will turn into a black hole. So according to popular modern stellar theories. So we are assuming that most stars do create, supernova, that do create this thing called a neutron star, which I will explain just shortly. First of all, the supernova in 1987A, the big story years ago, in the Large Magellanic Cloud, astronomers think that there's going to be probably a neutron star there forming out of that stellar explosion because of the neutrino flux that they saw, which is hinting that it will be such an object there. Okay, this is, remember this drawing from last time, the fork of stellar evolution. Last time we were talking about stars along this fork right here, planetary nebulae and white dwarfs, stars with intermediate masses. Today we're going to go down here, and we're going to talk about stars that, large explosions, supernovae events, turning into a very small, compact, and quickly rotating object called a neutron star. A very exotic object, to say the least. First of all, when a normal star, such as, or a massive star, I should say, about maybe 5 to 10 solar masses, when the nuclear fuel is spent, exhausted, the collapse ensues, and first you get an implosion and then an explosion. The outer layers are then consequently blown into the interstellar medium, the ISM, and while that happens, the central core begins to shrink even more under its own gravity into a tiny solid sphere, a sphere of about 7 miles. The diameter exceeds no more than about 20 kilometers or so. When the core of a massive star fuses its way into iron, the reaction simply cannot continue. There's not enough weight to push the core even further to continue the nuclear reactions. Here we're talking about a star with masses ranging from 8 to 20 solar. Now, when iron 56, that's what the type of iron, needs extra energy to fuse, it needs energy from the outside, but the problem there is none exists. So if you apply Kepler's laws to the gravitational mass, as far as we're talking about that, the iron core keeps on accumulating until it reaches about 1.44 solar masses, the critical limit. The electron degeneracy pressure that had been supporting it against gravity just simply peters out. So as a consequence, the object within continues to collapse even further. And there it's self-explanatory. We're talking about here the events that curtail for the neutron star. During collapse, the electrons and protons, they merge to form neutrons and neutrinos. Neutrinos are something that could be responsible for the precursor to a supernovae. A neutrino flux is what scientists see before a large star explodes. So that is sort of like a distant early warning device that tells astronomers that something is about to blow. So after some scattering, the neutrinos escape, and this is what induces the supernova explosion. There is a principle called the Pauli exclusion principle after an Austrian scientist. The collapse cannot continue any further according to this principle. In it, it states that no two neutrons can occupy the same place and quantum state at the same time or simultaneously. In a sense, this resurrected ultra-dense object becomes a 10-mile wide neutron because it has the same density as the nucleus of an atom. Astronomers have coined it. As I said before, a neutron star, in fact, it was Sir Fred Hoyle, English astronomer, who coined that phrase. In the physical realm, in some ways, it has the properties of a planet, but they call it a neutron star, so don't ask me why, but I think a neutron planet might even be more appropriate. A super hard shell around the outer core, and there's a crust that encases a zero viscosity superfluid within. At least 1,800 have been detected through their emissions in radio wavelengths and as strong emitters in X-rays. In fact, there's one that is pulsed in gamma rays, which I think I have some information on that in a little while. In fact, recently, and here I have it right here, in 2009, the Fermi Gamma Ray Space Telescope located a pulsar about 4,600 light years away in the constellation of Cephus that pulsed only in gamma rays. Studies have been done in our Milky Way galaxy and both Magellanic Clouds as far as locating these tiny animals, and they are found mostly along the galactic disk, right across here, which is quite logical. That's where most of the stars are. Some, however, are spread out across vast distances as a result of the supernova kickstart. To say the least, they are extreme objects. They are the astrophysicist's ultimate cosmic toy, excluding black holes, because neutron stars are more tangible. They're an object. They can actually, more sense, visibly see what is going on. So neutron stars provide a unique glimpse into the realm of the field of astrophysics that cannot be duplicated in a terrestrial lab. So getting back to the shrinking, some of them, by the way, are spread out here perpendicular to the plane. These are the ones that have been kick-started from the supernova explosion and are racing out of the galaxy at super high speeds. So after all this shrinking and downsizing, your typical neutron star will have acquired more than a sun's worth of material. Oops. Two equivalent masses of the sun, which is right here, the neutron star. At least that is what most astronomers agree on. Some say a little bit more, some say a little bit less. Now, according to the Oppenheimer-Volkoff limit, 3 solar masses is considered the upper limit for a neutron star. Because it is so dense and super compact, 1 teaspoon of this neutron star stuff on Earth would tip the scales at about 1 billion tons. Not sugar, by the way. That's not neutron star stuff. Yeah, the spoon would bend too. Chris couldn't do any computer magic here. And here's another analogy. Mount Everest. You can take the material that makes up Mount Everest and compress it into a sugar cube. And that's how much a neutron star material would weigh if theoretically you can get on its surface and scoop up a sugar cube's worth of neutron star material. And if you were to take matter from deep inside one of those dense objects, you would be able to compress the entire human population into the size of a sugar cube. That's how dense they are. Density comparisons, water, sun, and you can see how it goes up quite a lot. The white dwarf, again, a very dense object, but not as dense as a neutron star. And basically that's like 10 to the 14, 10 with 14 zeros after it, multiplied by 7. So it's super hard. Another mind-boggling reality is their ultra-fast rotation periods. As the progenitor star collapses prior to the supernova explosion, the inner core gets revved up to immense speeds that would make planetary and normal stellar rotations really pale in contrast. And this is taking into account the laws, including the conservation of angular momentum. The pulsar at the heart of the Crab Nebula seen, I believe that's an X-ray light, spins at a leisurely 33 times a second. That is considered sluggish. So you have this 20 kilometer sphere, or 10 miles, rotating at 33 times a second. This is why astrophysicists love to delve into these things. The fastest confirmed pulsar, which is in a globular cluster, Terzan 5, which is at the center of our galaxy, sits at the heart of the galaxy, rather, is an eclipsing binary radio source that spins at a blistering 716 revolutions a second. And there's another one even faster than that. Another radio source was clocked by scientists at Cornell University, but the signal is only tentative because the signal was seen at only one occasion at 1,122 hertz. That's the same as revolutions per second. And there's a spider on my sheet here. My gosh. Anyway. The closest one, Calvera in Ursa Minor, only 250 light years away, is isolated high above the galaxy. It is bright in X-rays, but dim in optical. And astronomers are questioning whether it's a new class of star or neutron star. The neutron star's small size and high density can generate intense magnetic fields as well. The origin of any magnetism stems from the progenitor star itself, the star that went supernova. Another comparison about magnetic fields. You got the Earth's magnetic field, they measured it in Gauss or Tesla, 1/2 or whatever, 0.0005. An MRI magnet inside the hospital, inside the MRI, 32,000 Gauss. Of course, the largest sustained magnetic field in a lab, 40 Tesla, and a magnetar, which is a type of neutron star, perhaps the most highly magnetized object in the known universe at 10 to the power 13 Gauss. A neutron star that has a directional magnetic axis that sweeps past the Earth is called a pulsar. Their point to make is that the magnetic and rotational axes of a pulsar need not be aligned, such as true north and magnetic north here on Earth. So you've got the rotational axis of the rotating object, you've got the pulsar's magnetic poles here, and they're just slightly off balance. And what happens is that when the pulsar, with its lighthouse analogy, sweeps past the Earth, then astronomers pick it up as a pulsar. If not, then we don't see nothing. We don't see those pulses. They're also called spin-powered pulsars, because the source of energy happens to be the rotation of the neutron star itself. So what happens here is that as a neutron star spins, the jets of material are traveling near light speed or relativistic speeds. These stream out above their magnetic poles, like so here, and they get concentrated into these, I guess, vortexes or death rays of light here. These are very highly intensely powerful beams of energy here. The jets create intense beams of light, and like I said, they're very similar to the lighthouse technology, the lighthouse beam on a lighthouse, except they're much more powerful. One of these beams, when they sweep past the Earth, instruments here detect the energy as blips, so that's when the astronomers call them simply as pulsars. So a pulsar is a rapidly rotating neutron star. Some do emit X-rays, like at the one at the heart of the Crab Nebula. Now, sometimes astronomers call them hotspots because temperatures at the magnetic poles are much hotter compared to other areas of the star's surface. So you got the hotspots right here, and you got the general surface, the rest of the surface of the neutron star. A word about neutron star temperatures is that when born from a supernova explosion there shortly after, the surface temperatures can reach as high as 1 billion degrees. That's 10 to the power 11 Kelvin. During this period, the compact object will obviously glow in X-rays. But since it emits a large amount of neutrinos, vast quantities of energy are carried away, so the neutron star starts to cool off really quickly, and this happens within a couple of years. This causes temperature to fall substantially within several years to a balmy 1 million Kelvin. Now, as far as general relativity, this, if you like to talk about the warping of space-time, this is great for Einstein's theory of relativity. A pulsar's gravitational field, anyone can be challenged on this one here, can act as a gravity lens, bending the radiation given off by this stellar corpse. It distorts space-time immediately around the dense object, the compact object. This lets astronomers to get a glimpse of the rear surface of one of these neutron stars. The gravity is so intense and so strong that an object, if you were to drop it from only 1 meter above the surface, would accelerate to 2,000 kilometers a second. That's 7.2 million kilometers an hour. In fact, if you could take a marshmallow and hold it above, if you could theoretically stand on a neutron star and take a marshmallow and just drop it, it would have the explosive power of an atomic bomb. So much for the power of the marshmallow. Definitely out of the question as far as landing humans on one of them. Now we go into the very complex part of the inner structure of one of these things. First of all, the surface. We'll start on the top. There are just ordinary atomic nuclei, and I'll just look at the picture or the image itself. Again, self-explanatory. Ordinary atomic nuclei that are mostly iron, because iron has a high binding energy per nucleon, so iron could stick and coalesce together quite easily. It is crushed into a solid lattice with a sea of electrons flowing through this lattice right here. These are the iron atoms here, and the electrons are flowing through this lattice here. Any object that would hit a neutron star would destroy its component atoms and become actually part of the star, so it actually would melt together as one. Earth's escape velocity, I think is 11 kilometers a second, if I'm not mistaken. The escape velocity for one of these things is about 100,000 kilometers a second. That's 33% the speed of light, so we better have pretty strong rocket engines. If the surface is greater than 10 to the power of 6 Kelvin, such as on a young pulsar, it would be in a fluid state. A fluid, I'm saying this rather loosely. On older, cooler neutron stars, which is less than 10 to the power of 6 Kelvin, the surface is most likely in a solid phase. The atmosphere, well, it doesn't show here very much here. It is only, well, it depends on what source you're reading, about 1 meter thick. Some sources say only 10 centimeters thick. And it is fully controlled by the magnetic field. The atmosphere is basically carbon, which is the leftover from the progenitor star. Below the atmosphere is a crust, which is hard and ultra smooth. It is about 1 kilometer thick, right here. Not very thick. We're looking at a very relatively small object, don't forget. We're not looking at a planet. And the maximum irregularities are about 5 millimeters. The gravitational fields there again shape the crust. So this would be a bobsledder's dream there. As we travel inward, the nuclei begin to have an ever-increasing number of neutrons. On Earth, these neutrons, they would quickly decay. Neutrons have a tendency to decay rather quickly, but the huge pressures on these neutron stars keep these neutrons stable. Still deeper, as we go deeper into the inside, the free neutrons are leaking out of their nuclei, and astrophysicists call this point is the neutron drip. Here there are nuclei, free electrons, and neutrons in this area right around here. Now, closer to the core, the nuclei become still smaller. There's a question mark because the core is still really not, it's poorly understood. We don't really know what material is in there, but we do have theories. At the core, the nuclei disappear altogether, leaving a mixture of densely packed neutrons, a sprinkling of protons and electrons, in a liquid-like state called rather romantically neutronium, which was also used in one of the Star Trek episodes, but it is not an official name. The existence of high-energy particles such as pions and kaons may also complement this mixture. You have to remember that there are no stable atoms or nuclei in this area here because of the intense pressures, only elementary particles such as quarks and electrons. Neutronium, by the way, is the unofficial name for the densest possible type of matter outside of a black hole. So we're in this equation, we're just forget that black holes exist. The 10% quantity of electrons and protons provide a supply of neutron formation within, which balances the neutron decay, besides the strong pressures. About the superfluid core. It's superdense matter that is still poorly understood. It is a phase of matter where bizarre effects are observed. The viscosity is 0, and temperatures are about 100 million Kelvin. Here it is that scientists think are vortices that migrate outward as the neutron star spins down as it starts to get old. It spins very quickly, and as the neutron star ages, it starts to slow down, but very, very gradually over hundreds of millions of years. It is here that scientists think are vortices that migrate outward. So I think I better bring that back here. They migrate outward from the interior, going up, and they attach themselves here to the crust, to the outer crust and the outer core of the neutron star. So when these vortices reach the boundary between the core and crust, they become pinned to the crust. They become stuck to the bottom layer. The spinning action keeps the core and crust spinning as one. And what happens is a frictional drag is created between the core and the crust. When the stress becomes great enough, the vortices then unpin from the crust, and they fall down because of the drag, the stress. And observers on Earth record a brief decrease in the spin rate, and this is what they call a glitch. Other mechanisms may be responsible for these glitches, such as a starquake, but a starquake doesn't have enough potential energy to be responsible for such a thing. It was thought that starquakes caused this about 15 years ago, but this vortice theory here seems to be more credible. Whichever one it depends, it all depends on the presence of a superfluid core. And just briefly, here we have the electrons in here, the iron core. These are the vortices here. They're sort of like mini cyclones. And you got your magnetic fluxes here. These are the vortices that travel upward to the core and then snap and then fall back down again, causing a change in the rate of the spin of the neutron star. Neutron stars are not only solitary wanderers. Some are actually found in binary systems, maybe about 5%. Combinations can include two neutron stars together, a neutron star and a black hole, a neutron star and a white dwarf, and a neutron star, and as shown here, and a regular star accreting material from a blue giant. The immense gravity of a pulsar, i.e. neutron star as well, pulls material from the companion right here. And this sort of acts as like a spinning top. You give it more angular momentum as it starts to accrete material. During the accretion process, the material becomes extremely hot and starts glowing in X-rays. The accretion phase can also spin up a pulsar and give it new life as far as angular momentum is concerned. The spin rate will increase by several hundred revolutions a second, and it is during this chapter in a pulsar's life that it graduates to something even more fierce, and they call this a millisecond pulsar, or an MSP. These MSPs can serve as ultra-precise and stable timekeepers. They can yield information regarding the effects of general relativity, such as the warping of space-time and fundamental particle physics. After all, neutron stars are actually nature's biggest particle accelerators. And the accretion geometry, basically it accretes material from the accretion disk here. It gets trapped in this magnetic flux here and it concentrates right into these poles here. This is the rotational axis. And you can see they're not misaligned by very much. And this is what causes this torus all around this particular neutron star, and sometimes it gives it new energy. So these things are constantly going over millions of years. To date, about 150 have been found in our galaxy. These are the millisecond pulsars. 90 of them, of those 150, are tightly clumped in globular clusters. One final thing regarding their slowdown time, it is constant and very minuscule. As an example, one which rotates in 1 second, in other words, if it takes one revolution in 1 second, which is quite slow for one, after 1 million years, it would decrease in speed down to only 1.03 of a second. That's how perfect these things are. And this is as close as you'll get to being eternal. This one here is an artist's illustration of a magnetar. This one, supposedly, this one here, SGR 1806-20, is about 50,000 light years in the direction of Sagittarius at the center of our Milky Way galaxy. It blasted our ionosphere on December 27th, 2004, and the blast took only 1/10 of a second to rip off the top layer of ionosphere. But the amount of energy, just to give you an example of how much energy are in these things, in 1/10 of a second, it is the same equivalent amount of energy as the sun would give off in 150,000 years. So 1/10 of a second, it gives you an idea of how powerful these things are. So why study these beasts? Here we are, the M1 pulsar in different optical wavelengths. I chose this slide as far as research is concerned. The same reasons why astronomers study other useless phenomena in this universe of ours. Because we are simply curious. We want to know about the properties of nuclear matter making up these exotic objects. And we are curious to know how relativity affects electromagnetic and gravitational fields that move through space at high speeds. We have two neutron stars here merging together. They eventually will coalesce, perhaps to form into a black hole. And this is at this point, when they merge, they will cause what is called a GRB, or a gamma ray burst, which is seen across vast distances of space. Of course, this is the warping of space-time like a bed sheet or a fabric. And as these two get closer and closer, they may evoke gravity waves, which astronomers are still looking for these gravitational waves. They haven't found any yet, but they do have indirect evidence. Pulsars also give us a new insight on timekeeping. They are the most accurate cosmic clocks in the universe. They are more accurate than the atomic clocks here on Earth. Another problem is, how do you accelerate 2.7 octillion tons, that's 27 with 26 zero after it, from a near standstill to over 1,800 kilometers a second? That's 4 million miles per hour. Since neutrinos are emitted from an exploding star's core, just before a supernova explosion, we can tap into the power of the neutrino, I was thinking about this, to provide quick and efficient transportation to the star using neutrino power as our propulsion method in the future. It was in 1934 that Walter Bade and Fritz Zwicky proposed the existence of the neutron star, and they were right. They wanted to know what was behind the supernova explosion. And one last item of historic note before I conclude. Oh, there's another image here of the melding or of the neutron stars. They start at far distances here, and they gradually coalesce, creating a gamma ray burst, and then you probably have a black hole. One last thing before I go, on a historic note. In 1967, Jocelyn Bell, at that name, Jocelyn Bell Burnell, and Anthony Hewish. Jocelyn Bell at that time was a postgraduate student at Cambridge and also now a British astrophysicist. She picked up an errant signal with almost perfect regularity, 2,300 light years away in the constellation of Vulpecula. Assumed that it was spurious noise at first, such as man-made, radio equipment on Earth or even a satellite, but then later the hypothesis was discovered. There was a second proposal. It was a little bit on the wild side, but they figured perhaps it was a signal from an advanced civilization. They called it quite jokingly LGM-1, which meant Little Green M-1. Little Green Men, I should say. Eventually, it was found out that the radio emissions from Pulsar, which is now known as Cambridge Pulsar CP 1919, was from one of these objects itself. It wasn't from any advanced civilization. It was the first discovery of its kind back in 1967. And that was the year, I guess, when the World's Fair came to Montreal, and I think that's when the Leafs won the last Stanley Cup, I believe.
That long ago?
Yeah, it's ancient, isn't it? According to Bell, other scientists could have discovered pulsars before her, but their observations were either simply ignored or disregarded. Unfortunately, it was Hewish and Martin Ryle, who was the other colleague that was involved in this discovery, won the Nobel Prize in 1974 for their theoretical info about these objects. And sadly, Bell was left out for the award because at that time there was this male chauvinistic thing that men ruled science and the women were kind of left out. But this did not alter her love for astronomy. She persisted. Over time, she left radio astronomy to pursue the world of X-ray and gamma-ray astronomy, and also continues to give talks and lectures about the universe. So although she was singled out for this prestigious award, she did make a name for herself as far as pulsar astronomy was concerned. So eventually, I think officially she did share the title or the Nobel Prize, but initially she was kind of left out, and finally, all in all, it was a happy ending to the story. These are pictures back in 1967, and you couldn't get the internet running, I guess, eh? Okay, so we didn't have any recent photographs of the two of them. So, and that concludes my talk. Thank you.
Thank you, Richard. Very interesting topic. Next up, to brief you on the latest developments in astronomy, Al Scott.
Okay, so I've got a few little tidbits for you. The first item of news I'd like to share with you is the WISE telescope. Was launched in December of 2009 and is now sending back its first images. WISE is the Wide Field Infrared Survey Explorer. It's a 40 centimeter infrared telescope, and you can see it there in the bottom. What most of that you see is a big cryogenic dewar, basically of solid hydrogen to cool the detectors, so that the thing can actually detect the thermal emissions from warm dust in the universe. So this thing has a 6-month mission to map the entire sky in the infrared to about 6 arc seconds of resolution. And here are some of the pictures it's returned. You can see the Andromeda Galaxy there. The color coding is 3.4 micron light is blue, 4.6 micron light is green, 12 micron light is orange, and the 22 micron band is red. So it's a 4-band multispectral imager. So you can see the dust lanes glowing in the long wave radiation. The 22 micron stuff is from relatively cold dust, less than 300 Kelvin, for example. But it's warm. It's emitting in that wave band. The blue is from the hotter star forming zones. But it's a really neat picture. The other thing is comet siding spring. It's called. Its closest approach is 1.2 astronomical units. And you can see that it's glowing at 22 microns as well. It's warm, well, not warm as we would think of it, but warm for things in space. It's really a nice picture. And in the bottom corner is a much further image. It's the Fornax galaxy cluster, 60 million light years from Earth. It's kind of a neat picture showing the star-forming regions. And you can see the one, is there a pointer on this? Center one. You can see the one red galaxy there, a big red galaxy, and we have a bunch of other smaller galaxies. So this one's got a lot of older stars, and these ones would have a lot more younger stars in them. The second thing I want to talk to you about, this is a far ultraviolet image from the International Ultraviolet Explorer of the system. It's a close binary system, T Pyxidus, in the southern hemisphere constellation Pyxis the Compass. It's a recurrent nova, actually. And what a recurrent nova is thought to be is a white dwarf star which is accumulating mass from its binary companion. And as it accumulates the mass, it goes through a massive nova explosion, big thermonuclear explosion on the surface, blows off a whole bunch of mass, and creates these shells of stuff that come off of it. And Hubble has actually imaged the shells and can try to estimate the mass in these things. Now, the interesting thing about this nova is a recurrent nova. It has an explosion approximately every 20 years, recorded first in 1890, 1902, 1920, 1944, 1967. The last one was in 1967. 44 years overdue for its next thermonuclear explosion. Nobody knows why. So what astronomers did was they modeled these ultraviolet spectra that they've taken and compared it to state-of-the-art models of disks being circulating around the white dwarf star, tried to model the radiation intensity and the sizes and everything, and tried to play with the parameters of their model to get the best fit to what they actually saw. And the best fit turns out that this is basically most of the radiation they're seeing in the ultraviolet is coming from the accretion disk, not the star itself. The energy in this disk is crunching down onto the stars, creating ultraviolet light. The white dwarf star seems to be very close to its Chandrasekhar limit, which means that it's close to going supernova. The Chandrasekhar limit is the amount of mass that you can put onto these things before gravity overcomes the electron pressure, like we just heard before, and it turns into a neutron star or a black hole. And the amount of mass that the thing should be accreting to make this sort of UV flux is something like 2 × 10 to the 17th grams per cubic grams per second, which if we again relate it to Richard Alexandrovich's talk, that's about a liter of neutron star mass every second smacking into this thing, or 3 billionths of a solar mass every year. And the distance of this system from our solar system through the model is less than 1,000 parsecs. And that's significant because the closer distance means that the ejected nova shells that Hubble have imaged are actually smaller than they previously thought. And that means that this thing is actually gaining mass rather than losing mass through its recurrent explosions. And if it's close to the Chandrasekhar limit and it's gaining mass, that means it could go over that limit. And this would cause what's called a type 1a supernova. And if a type 1a supernova explosion occurs within 1,000 parsecs of Earth, the gamma radiation emitted would fry the atmosphere, dumping as much gamma radiation as approximately 1,000 simultaneous solar flares would give us. And the production of nitrous oxides in the atmosphere from all this intense radiation would completely destroy the ozone layer. So, interesting times. Nobody really knows what's going on. In a separate study, Chandra has actually made a survey of 5 nearby elliptical galaxies plus the Andromeda Galaxy. This is some X-ray emissions from the Andromeda Galaxy. And what they're trying to do is, we basically know what the rate of type 1a supernovas is over time in galaxies of various sizes. We have a rough idea, 1 per century or something like that. And using the models of these systems, we know how much X-ray emission these galaxies should be giving off. These are very luminous in the X-ray from their accretion disks. They should be very luminous in the X-ray. So we know roughly how many there should be in a certain size of galaxy to produce the observed supernova rate. So we can look to see, do we get enough X-ray emission to correspond to the number of these systems we expect? And what they found from this survey is that there's 30 to 50 times less X-ray emission than what they'd expect, which means that white dwarf accretion scenarios are not the likely source of type 1a supernova, or the models are wrong. The other possibility that astronomers think is 2 white dwarfs merging could cause a type 1a supernova. And that has implications for how we measure distances in our universe, because we treat type 1a supernovas as standard candles, because we think that it's when a star goes over its Chandrasekhar limit, it has always the same amount of mass in it, so there's the same amount of energy that should go into these explosions, so they should be the same brightness no matter where they occur in the universe. Now, if this isn't the mechanism for type 1a supernovas, if it's actually 2 white dwarfs of different masses colliding and overwhelming the Chandrasekhar limit that way, then the energy emitted in a type 1a supernova could be somewhat more variable than we expect. But, this is an early result, so nobody's really quite sure what this means. An open question remains then whether or not these merging white dwarfs are the cause, because no one's really seen many binary white dwarfs. The problem is, of course, is they're difficult to see. So what this is going to do is it's going to spur a search for more binary white dwarfs to see if there are enough binary white dwarf systems to explain the supernova rate that we know. So again, some interesting unsolved issues to worry about. So maybe it's not likely that this is actually going to go supernova at all. So there's some interesting thinking that needs to be done. And my last item, this is actually a Hubble photo. This is the object called P2010A2. It was discovered by the Lincoln Near-Earth Asteroid Research, or Linear Sky Survey, on January 6th in the main asteroid belt. And they thought, oh, a comet in the main asteroid belt, that's very rare. But interestingly enough, the nucleus is separated from the tail, and you never see that in a comet. Just for scale's sake, this nucleus is about 420 feet across, or 460 feet in diameter. So this is high zoom. What they think this is, rather than a case of an orbiting comet, what they did is they put a spectrometer on this tail to look for the comet emission lines in the gas. There's no gas emission lines in this tail. This is all just dust. And what they think this is they've imaged the aftermath of an asteroid collision. And you can see there's these interesting filaments, as though something might have come in and crashed into it and blown a whole bunch of dust off of the asteroid. So it's quite a neat picture and kind of a serendipitous discovery. Whatever it is, it's somewhat unique, and it's a really neat image. And that brings me to the end of our 10-minute astronomy news update. Thank you.
While you're walking around the calendars.
And one more thing I want to mention. We do have a few calendars left over. There's a bunch here that are going to give away as door prizes. If you don't get one as door prizes, please come and take one. They're very, very cheap. I don't want to discount them too much more, because then the people that paid full price would be upset. But this all goes to the society, and we'd love to use your money. Thank you.
Thank you again.
Okay. Just a brief little thing before we get on to the observations section of the evening. Eric will be up here in just a moment, but I have one thing to show you beforehand. As you probably know, I'm kind of the rocket guy in the group. I fly rockets all the time. Take a strong interest in it, and I'm subscribed to a number of mailing lists and other things in the States that have to do with rocketry. So every once in a while, something turns up that's of interest to more than rocket geeks, and I thought you might enjoy this. It's some footage of one of the fairly recent launches. The announcer announces what payload's being lifted, but what I want you to watch for is not so much the rocket, but as it's traveling through the air, watch the atmospheric effect. This is really interesting. Can you roll that, please?
3, 2, 1, 0, and ignition and liftoff of the Atlas V with the Solar Dynamics Observatory,
Okay, so
learning
this is the
why
SDO
our
code.
star is changing our lives.
Atlas 5, this one. Watch this.
Steady state operating levels at 100% thrust on the Marty 180. Vehicle dynamic disturbances.
I'm just repeating it a bit here because it's so interesting looking. I gather from some of the talk that was going on around the release of this that the rocket was actually passing into what would be an apparent sundog. It was, ice crystal-y sort of day, and it's believed that this is a result of the shockwave off of the rocket rippling through the ice crystals, produced this interesting sort of diffraction effect that you saw there.
On the Atlas propellant utilization system.
Just a little bit of trivia.
Operating pressures continue to look good.
This will cut off in a moment. The rest is just
Flight
boring
control data
rocket
is
stuff.
smooth,
Nothing.
as expected for this portion of atmospheric flight.
There we go. So next up, Eric Kujala is going to come up and speak to us a bit about some images of M31. Welcome, Eric.
Thank you, Bill. First, I'd like to thank Al Scott for introducing my talk. Last month, I noticed an image on NASA website. I don't just look at NASA websites, but it's one image I saw, and I thought I'd bring it to your attention because I feel that this is a sort of a turning point in astronomy in a sense, because we've been used to looking at images in the visible portion of the spectrum for since Galileo, and now that seems to be really shifting towards the infrared. And what I did is take 3 images from of the Andromeda galaxy, M31, Messier 31 for those who don't know that, and I posted them here, and I wanted to show you each image and the difference between the 3. Okay, so if we go for the first image, this was borrowed from Sanjeev. Thank you, Sanjeev. Beautiful photograph, and it caught my attention and was one of the more recent photos of Andromeda, so that's why I picked this one to start my brief talk. Sanjeev took the photo, I believe it was in November or December, and he had modified his camera to be able to take the photo in closer to the infrared portion of the spectrum. He modified the camera to do the photo, and I studied this one first, and then decided to look for a higher resolution image done with the Hubble. But what I noticed was how good his photo was compared to Hubble. I mean, Hubble is, you're talking about billions of dollars from a space-based telescope, and then I looked at his, so I really appreciate the local imaging that you folks do. It's incredible the quality that you're getting with only a few $1,000s worth of equipment. And if we could go to that Hubble image, please. So this is the one that I downloaded for Hubble. Obviously not the same resolution that they would. I mean, this is a lower resolution image of what they took, but when you compare the photos, you see that there are more stars in this photograph, but appreciate the different circumstances that they're taken in. Now, I was talking about visible light, and we've traditionally looked at the stars and the galaxies in the visible light spectrum, but the electromagnetic spectrum gives us a whole new range of ways of looking at these images, these objects. And if I could go to that graph, please. So here we have the visible light range, and the photos taken by Hubble are mostly in the visible range, but they go towards the infrared as well. And we have telescopes that cover most of the spectrum. I've learned recently that there is an array of radio telescopes now whose resolution rivals Hubble. That was interesting. At the other end of the spectrum, we have the Fermi Space Telescope that takes photos in gamma rays. They show different attributes of those objects. Richard Alexandrovich had a beautiful photo in his talk tonight that showed in X-ray and gamma ray and so on, and kudos to that. And we also have photos taken in the X-ray portion of the spectrum. For example, Chandra is doing that. But it seems that now infrared is where we're concentrating on. And the WISE, the Wide Field Infrared Survey Explorer, was recently launched and is now taking those photos. And could we go to that one, please? Here we see a lot more detail in the arms. And there's supposed to be a double nucleus that they've recently discovered in here as well. But what really caught my eye was just the number of stars that we see in the infrared. And Chris, if you could show us the comparison. So here we go from the visible light. Look at that difference. It's huge. Not nearly as much detail in here. Now, I am taking into account that this photo was taken under different conditions, but this is the future. And this telescope is designed to give us an inventory of the sky. It doesn't replace the other telescopes. It will help the other telescopes better see what is in the sky so that we can home in on them with the other ones. And I'm really looking forward to what the James Webb Telescope will do for that. And that is my talk.
Thank you, Eric. Thank you. Next up, observations this evening. We have a number of observation reports. The first one I'll speak to primarily because the contributor is still in Australia and couldn't be here for tonight's meeting. Roman, you may remember, headed down there for studies a little while ago. Every so often he sends us up some photographs that he's taken down under. So the first of these is taken across Canberra Harbour, and it just has the moon up in the corner of the photograph. Next one, a little bit more of a close-up, but taken from the same site, just with a bit more zoom. And the third, very scenic. Actually, this is now my desktop at work. I liked it so much. What is it? You can see the crescent moon up in the upper right corner. Otherwise, beautiful shot of a lighthouse. Okay, on to the next. Next up is, oh yes, Paul Commission.
Oh, yes. You remember last month I showed you Matthew 1, which is a galaxy located right in the middle of the Milky Way there in Cassiopeia, a place you wouldn't think of looking for a galaxy. Well, this month I'm showing you NGC 7772. Now, that's not much of a picture, and it's not much of a cluster either. But the reason that I'm showing you is this is in Pegasus. Pegasus is full of galaxies, all kinds of different galaxy groups, quasars, and things like that. This is the last place you'd be looking for an open cluster. But this happens to be there. So if any of you ever have a chance, when you're in Pegasus, this is relatively, it's small, it's only 5 minutes, but with a 6-inch or an 8-inch telescope, you could see it quite well. But I thought I'd show you, and I'm continuing this theme, that last month I showed you something that was out of place as far as galaxies are concerned. This is out of place as far as open clusters are concerned. Next one, please. Now, this is about the same size. This is NGC 7044. I just wanted to show you, this is in Cygnus. I wanted to show you, this is about what a normal open cluster should be. The other one is very sparse, but at least it's only there to as a cluster that is out of place. But this is how it should look like. This one was taken in Cygnus, and it's a much richer. This is how it should look like, rather than the other one that has about 6 stars in it. Anyway, okay. Thank you very much.
Next up, Rolf Meyer to talk to you about some Mars observations he's done recently.
Okay, this was obviously January 23rd. Let's see, so there's this feature here. This is Olympus Mons, which is one of the very large volcanoes on Mars. And so these are images in red, green, and blue, and you can see that in blue light, things like cloud features show up very well. So what you're seeing here actually are the clouds around Olympus Mons. And if you look very carefully, there's a dark spot in the middle where its top is kind of sticking up. Basically, there's quite a few volcanoes in this part of Mars. And this is what's called the Tharsis area, and more volcanoes here. So when Mars is rotating this way, okay, so what you have is you have more clouds kind of in the afternoon sky, if you like, of Mars. This is upside down with south at the bottom. That's because, even though it doesn't matter anymore when we take pictures, people have been observing Mars for so many hundreds of years through inverting telescopes that we always like to show pictures of Mars with south at the bottom. For the first time in a long time, the North Polar Cap is visible to us. The South Polar Cap is kind of facing away from us. Usually we don't see the North Polar Cap because of what's called the North Polar Hood. But you notice also that there's kind of a donut of dark stuff here where it's very much dustier and dirtier on the polar cap. There's also another sort of tall mountain here called Elysium, and you notice it's more in the morning part and it doesn't have the cloud yet. So here in the evening is where you'll see a lot of the clouds. Next, okay, this was about as close to opposition as I could get. Closest approach. Mars didn't get too big this year, but we also had very poor weather, and just couldn't get too many observations of Mars, so I took a number this night. You'll see also very interesting that just above the north or the south polar, this is the North Polar Cap, is this reddish area. And very interesting that's usually not seen either because of the North Polar Hood, and again this kind of a donut shape there, and more clouds in the kind of afternoon, evening part of the Martian day. So I actually took a number of images that night. And I put them together into kind of a short animation. I guess that would be the next one. Just showing Mars rotating over the space of about an hour and a half. And you can see that the clouds kind of tend to be on that side anyway. And then this other cloudy area kind of coming into view. And this reddish area kind of rotating. And this is the feature called Sinus Meridiani, which is the prime meridian of Mars. Next slide. And this was probably one of the better images that I was able to get February 16th. Of course, Mars is shrinking quite a bit now. You can see again the red, green, and blue. And blue is mostly featureless, except the clouds show up very well. And also, this is the very large, obvious feature on Mars called Syrtis Major. And it's, all these dark areas are mostly rubble and rocks that have been kind of scoured of the more sandy areas. And this is where the sand gets deposited. And the appearance of these features changes from year to year. For example, this area here was a very prominent dark spot a couple of years ago, but now it's a lot of sand has been deposited there. Sand or dust or whatever you want to call it. Again, this reddish area there. Okay. Oh, this is called Hellas. This is kind of a depression, and it's often very bright from clouds and kind of more like fog, I guess you'd say, because it's a low-lying area. Next. Okay, and this is 3 views of basically the same area of where December, January, and February. In this, because the Martian day is slightly longer than ours, in the space of a month, you get the same area visible to you. So in the at the roughly the same time of night. So in the space of a month, you'll see a slightly different side of Mars every day. Then in a month, it'll be looking roughly the same again. So the differences here are that you can see around December, of course, Mars was a lot smaller, and it had somewhat of a phase. But these next 2 pictures really show the difference in seeing more than anything, because the diameter of Mars was about the same. So this, on January 9th, a night of relatively poor seeing, which is actually kind of normal for Ottawa. And on February 16th, much better seeing. But interestingly, on February 16th, it was only clear for about an hour and a half, and I just decided to take a chance anyway. So, always try and take a chance and observe when you can. By the way, this again is the Elysium. I guess it's a volcano. Is Elysium a volcano, Simon?
Yes.
Yes. So that's again in the evening. You have these clouds hanging over it. Even in this one, it's kind of visible. I guess in this one, it's probably in the dark. Okay, that's it. Oh no, it's not it. One more. Okay, so this is. Oh yes, good news. Good news. There's sunspots are back. So I don't know. Did anybody see this sunspot? This was about 3 weeks ago. And again, it was cloudy most of the day, and this was only about 2 hours before the sun set, so I was able to get this. This is actually a very large group. So if anybody saw that, I think it's gone now, but maybe more spots are on the way. So keep looking at the sun.
Great. Thank you very much, Rob. Next up, Sanjeev with some images of a horse head.
Thanks. Well, I don't have much to show you guys today because the weather wasn't very cooperative in February. But I want to show you 3 pictures of the horse head that I did, and they're all with 85 millimeter refractor, a small refractor. This one I actually did in November at FLO, and it was with, it's a cropped image. I did it with my Canon 40D DSLR, and the other 2 images, what I did was I cropped them all so they show you roughly the same amount of sky. So, okay, so that must be very familiar. That's the third, one of the stars in the belt of Orion, Alnitak. It's the easternmost star. That's the Flame Nebula. There's the Horsehead B33, and this is a reflection nebula here as well. Okay, so now this one, this is, by the way, this is about 90 minutes of data. This is only about 30 minutes. This is from my backyard. I did this in February. I don't know if you can see much there. It looks pretty dark on the screen. But this was through an H-alpha filter, and I live in Canada, so there's a fair little bit of light pollution there. But I did this from a backyard with an H-alpha filter, and it obviously lets in a lot less light through. So you can see just from the star here the difference, right? This is pretty much the full visible spectrum, and the H-alpha filter lets in a lot less light. And then the next one I did was I actually used 3 different narrowband filters, and so I took this data from here, the H-alpha filter, and then I also took more exposures through an oxygen 3 filter and a sulfur 2 filter. And then this is a false color image because the H-alpha has been mapped to the red, the oxygen 3 has been mapped to green, and the sulfur 2 has been mapped to blue. Now, if you look at the spectrum from about 400 nanometers to 700, that's the visible spectrum. The sulfur 2 is actually a deeper red than even the H-alpha, so it really should not, if you're going to go for a more of a realistic representation, you would be mapping the sulfur more into the red part of the spectrum, but you had to have something for blue. So this is actually, it's called the HOS palette, so people sometimes use this in narrowband. Again, it's a false color image. I want to make another point, but I can't because I wanted to show that this is actually a slightly larger image scale than these 2 images, but Chris had to put these things in PowerPoint, so the image size is a bit altered. So I'll come back next month and make that point, but it's a very important point about what happens when you use different cameras with the same telescope. Because the SD10, that's the CCD camera that I used for these last two pictures. This is also from my backyard, by the way. So the SD10 has slightly bigger pixels than the 40D. The 40D has smaller pixels, but what that does is when you use smaller pixels, you're using more pixels to show the same amount of sky. What it means is that each pixel will show a smaller piece of sky, so you're actually going to see a bigger looking image. You're going to get a bigger image scale, and that's actually a pretty important point, but it's not quite apparent in these pictures. But anyways, that's what I was trying to show as well. So that's basically it.
Very nice, thank you. Thank you very much. All right, next up, our lunar challenge for the night. Murray Campbell's here to talk to you.
Okay, I apologize for the way I attire. I don't normally wear a tie, so... Okay, could you advance it then? Okay, let me introduce you to Billy Rasc. Okay, Billy is a bit of a black sheep of the family in craters. In this astrophoto of the day, where am I pointing? Yeah, that's him. There you go. Billy's not a bad chap. Billy's larger neighbors are detectable in a good pair of binoculars, particularly highlights of the highlands areas, the regions. And the smaller impact craters and that develop and more discernible in the larger telescopes that you use. So, today's challenge, Isabel Williams number 124. You can find it in the Ruckel chart there, 40 and 50. So Billy, Raymond Billy, and Billy D. So, scalable challenge for the folks. Okay, next one, please. Okay, you can find Billy and the family, Billy the kids plural, down here in the southwest, around the ocean, Hummerum, all the neat stuff, and dark crater there is your key find if you're using binoculars and binoculars alone to find the area. It's Billy is the Imbrium period, and it's 46 kilometers size. Albedo is very dark, caused by the dark basaltic lava-filled floor. It's immediately detectable in telescope in contrast with light tones Mons Alpha. Next slide, please. Mons Alpha, because of Hanstein here. Hanstein, Mons Alpha, also known as the arrowhead. So Billy, the odd couple. Bright, dark, bright, dark, bright, dark. Further to this, you can see that the coordinates for the zone is 13 degrees 8 south, 50 degrees 1 west. So if you want to find that, plug that in and go ahead. The challenge, getting to the challenging part here, is one, the contrast of the neighbors. The neighborhood is rather large, dark tones, light tones. This Mons is an eruption, much younger than these two features. Bright as bright. Billy has a little friend, Billy D. For your larger telescope, folks, isolate Billy D and discern the cavity that comes down and a little rill, also known as rim. Your challenge, if you choose to accept it, is to find this 70-kilometer long rim rill and some of its neighbors and plot its charts and plots and find out where the other ones are as well. So for folks like me that have binoculars, you can see this giant area quite well. In a 4-inch scope using a 9mm Gary's 9mm eyepiece, this is very discernible and very good, the odd couple. And for the larger folks, 10, 12, 14, try to get Billy D and the rails. So that is it. Okay, thank you very much.
Thank you, Harry. Next up, your Deep Sky Challenge from Paul Commission.
I chose NGC 2158. Now, everybody knows the M35. Everybody looks at it and photographs it and all that. But it's reversed here. Actually, M35, no, you got it the other way.
The labels are misleading.
Yeah, that's okay, that's all right. It's a small, it looks like a very small open cluster, but in effect, it's bigger than M35 simply because of the fact that it's about 5 or 6 times farther away. M35 has about 200 stars in it. NGC 2158 has about 900 stars in it, so it's much more thickly populated. It's down there. Look to your left, bottom left there. It says M35, but actually it's mislabeled. That's 2158. So you find it about it's from the center to center. It's 26 minutes, 26 arc minutes from center to center, and it's southwest of M35. It's an interesting thing to see. As I say, most people neglect it because they're so interested in M35. So that's the challenge of the month. Thanks.
Thank you, Paul. And next up, we have Simon Hammer to present some images from the Selene mission.
During the past year or so, the European Space Agency and the Japanese Space Agency have both successfully pushed the edge of the envelope in terms of very high resolution imaging of our planetary neighbors. So tonight I want to present you some spectacular high resolution images of Earth's moon captured by the Japanese, one of the Japanese Space Agency satellites. If I say JAXA every now and again, that's because that's the shorthand for Japanese Space Agency. Now, some of these images are so detailed that frankly, they are the next best thing to being there. Next one, please, Chris. The JAXA satellite was variously known as Selene or Kaguya. Selene was more of a technical name. It stands for the Selenological Engineering Experiment, I think. But Kaguya was the name of a mythical Japanese princess. The images that I'm going to show you tonight contain many details that you will likely not see with an amateur telescope. But I think that they nonetheless help you to better understand and appreciate what you can see through your favorite telescope or binoculars. Next one, please, Chris. Now, Kaguya was placed into a polar orbit around the moon, and it was equipped with various cameras, including, interestingly, forward and backward-looking high-definition TV cameras. So what I'm going to show you tonight is a selection of still images taken from the HDTV movies that the Japanese Space Agency successfully processed to various degrees. And you'll see just how successfully they processed some of these. Next one, please, Chris. Now, all of these images will be accompanied by an inset image of the moon here with a white box which will move around over the moon's surface so that you know where we are geographically. So let's start looking south over the ever-familiar crater Plato here, on the north side of the Imbrium impact basin, which is what all this flat expanse is out here. You can see the scale of things. You can see the curvature of the moon. This means that we're looking at a pretty wide field of view here. Now, notice the very obvious slumping here on of the original crater walls and the flat floor that represents the lavas that flooded the crater and almost filled it to the brim, but not quite. To the south in the distance, you can see the floor of the Mare Imbrium. And this smooth floor represents the lavas that filled the gigantic hole that was left by the Imbrium impact. Lavas that left an alignment of mountain peaks, which you can see here. Starting out here, you can see the Strait and the Tenerife Mountains. Here's Mons Pico, which we'll come to again in a moment, and there is Mons Beta. And here, right on the horizon, are the Spitzbergen Mountains. And in fact, this alignment here represents the inner ring of the multi-ring basin, which formed during that massive impact about 4 billion years or so ago. Next slide, please, Chris. Now, look at the detail of these high-resolution images. Here, we're closing in, obviously, on Mons Pico, and again, we're looking south. Here, though, in the foreground, down here, it's a little low, but hopefully you can still see that there, at least from the back. These are the slumped cliffs of the southern rim of the crater Plato, and the resolution is remarkable. You can clearly see the scars on the original cliff faces made by materials sliding down the cliffs and into the original crater cavity. In midfield, here, we can see Mons Pico and Mons Beta here, poking up through the Mare Imbrium lavas, but we can also see some remarkable details. Note this small straight feature right here, straight linear feature. It looks very much like a narrow valley with one wall in shadow, that's the one to the right, and the other wall, the opposite wall, illuminated by the sun, that's the left wall. Notice how few impact craters there are in the Imbrium lavas. But what do you make of these chains of pits here? See that chain of pits there? And then this second chain of pits? Straight features and chains of pits are going to be a recurring theme in this evening's talk. Before I saw these Japanese Space Agency images, though, I'd never realized just how abundant they were on the moon. Next one, please, Chris. So here we are. We've zeroed in on Mons Pico. Two images here. Here's Mons Pico and here's Mons Pico. I don't know how they did this, but the Japanese Space Agency scientists have manipulated their satellite images to bring the viewer's sightline pretty much down to the moon's surface on this image here, without any appreciable distortion. If you don't mind, I'm just going to walk out in front and see exactly what you can see. It's difficult from the side here with the distortion that I'm getting to see whether or not you're actually getting the resolution here. They're a little darker than you would actually see if you were to go to the Japanese Space Agency website, but nevertheless, I think these will work. Now, while this image is itself amazing, take a good look at the resolved texture of the surface around these images here. It's a little dark. You may not be able to see this as well as I'd hoped. I was expecting to see rock, but this surface is remarkably smooth. It's covered with a thick layer of remarkably uniform dust. Now, this is the result of billions of years of gardening. That, by the way, is the technical term for the incessant micrometeorite bombardment that, over time, billions of years, pummeled the rock surface to a powder. Now, NASA has made it clear that the biggest problem for any eventual long stay on the moon will be dust. And I think you can see why. And again, this was never quite so apparent to me before I saw these JAXA images. Next one, please, Chris. I'll come back to dust in a minute later in the talk, and you'll be able to see perhaps even more clearly than that one there. That was a little disappointing at how dark that is. Now, moving to the southeast side of Imbrium, you can see where we are here. We can see the classically flooded crater Archimedes. There it is there. It's a flooded crater with the Spitzbergen Mountains here in the foreground. The simple impact craters, like this one here and these ones over here that you can see, the simple impact craters in the basalt lavas that flooded the Imbrium Basin are pretty obvious. But I want to draw your attention down to this corner here, to a set of closely spaced linear features. These things here, you can just see them, I think. And what they're actually made of alignments of what are best described as pockmarks. These things do not look to me like aligned impacts produced by meteors that would have broken up in flight. There's just too many of them, they're too systematic, and they're all identical in size, just too many coincidences. Now, planetary geologists interpret this kind of feature as a swarm of parallel fractures, or faults if you will, that may have guided lava and gas from within the ancient moon billions of years ago, making these aligned pockmarks volcanic in origin. Again, this is the alignment of pockmarks. There's another alignment there, and again, and again, and again. Now, as you'll see in a few slides' time, the pockmarks themselves are probably not classical volcanic craters. They're more likely to be collapse features. Bear with me for a moment, I'll explain that as we go. But again, this is going to be a recurring theme in these images tonight. Now, let's move a bit further south and gain some height. And the next one, please, Chris. There we go. So we've zeroed in here. We can much more easily now see the slumping on the inner wall of the crater Archimedes. You can see that slumping there, beautifully pulled out in this high-resolution image, with the slump blocks themselves being drowned by the basalt lava that flooded the impact crater. You can actually see the lava essentially like lapping up, if you will, right against those slump blocks. As well as on the outside of the crater, you can see an apron of ejecta, this stuff here, on the outside, that was thrown out during the impact. Now, because of the image resolution, you can also make out a variety of different sized craters that pepper the Mare basalts that flood the Imbrium Basin. You can see some relatively large ones here, if you like, and some of these really very, very small ones going down to almost beyond resolution, but not quite. Notice how, no matter how small they get, they do not form these linear alignments I showed you in the previous image. So these probably are impact related. Now, let's move to the edge of the Imbrium Basin itself, which will be out here. Next one, please, Chris. That's right, that's where we're headed. Now, the edge of the Imbrium Basin here, you can see it right there. It's knife-edge sharp at this location. Why? Because this is a large fault, rather like the Erdley Escarpment, if you will, on the Quebec side of the Ottawa Valley. And in fact, you can see a second fault out here in the Imbrium Basin itself. In fact, you could probably trace that same fault up through here. These faults were the mechanism that allowed the walls of the original Imbrium Basin cavity to slump into the hole created by the massive impact that formed the basin. Next one, please, Chris. Now, here's a very unusual perspective on the crater Tycho. The central peak here, in the middle of the crater, is impressive as it sticks up through the rubble of the crater floor. Note the minimal impact cratering within the crater, or the impact cratering, correct, within the crater, which is just what we would expect given that this is the youngest large crater known on the near side of the moon. Now, while we're looking at that crater floor, this high-resolution image really brings out the fact that the rocks are actually covered with a uniform coating of dust. Thin enough here that it can't quite hide the underlying rocky texture. That's why you see all this variation here. So there are lumps and bumps in here. That's unlike what we saw at Mons Pico, which admittedly was a somewhat darker picture, but in the Imbrium Basin. But the amazing thing in this image is the terraced crater wall in the far distance out here. These terraces out through here. And we can see that as though we were only a few kilometers above the moon's surface. Remember, the satellite was actually hundreds of kilometers high. And again, there's no distortion. So let's stay with Tycho. Let's move in and get an even better look. Next one, please, Chris. Oh, here we go. Now, here we're looking along the crater rim. Now, you can clearly see the steep walls here of the terraces. And you can also see the downslope scarring. See it here? There's downslope scars. And you can even see it out here in the far distance. And these scars were made by the landslides and slumping that gave rise to the terraces that rim the crater floor. But now look for the fine details. Notice these apparently rounded, illuminated objects through here. Those are boulders. You're looking at boulders, huge boulders on the moon. Next one, please, Chris. And here we're coming in even closer still, even a more detailed image of the same features. Notice here, that same rubbly appearance. That again is that swath of boulders. Did they roll down the slope of the crater? Or were they thrown out of the crater by the impact? Now, will you be able to see this in this image? Yeah, yes, you can. Notice here, this very fine layering. It's actually tilted and dipping away towards this terrace wall here. But you can notice a very fine layering. It does actually go up through here too, but this image, I'm afraid, in the projection is too dark for you to see it. You can actually see that layering here too, and here. Perhaps you can see it even better there. Now, let me not lose my place here. Okay, so now this is the moon. So this layering cannot be sedimentary layering because there's no water and there's no air, and there never has been. While it's not impossible that this represents layers of volcanic ash, it's far more likely that this is layering due to the settling of crystals in the global magma ocean that formed the early moon's uppermost 100 to 500 kilometers, and that cooled and slowly froze shortly after the moon had formed. And again, in this detailed image, we can see just how dusty these rocky surfaces appear to be. Next one, please, Chris. Now let's jump up to the northern polar region here, as you can see where we are there, where the craters are spectacularly imaged due to the relief that's brought out by the very low sun angle. However, this is not what I want you to notice. I want you to notice these things here. These linear, multiple, regularly spaced, and parallel fractures that cut right across the center of the image. Remember the similar array of linear features just north of Archimedes? Well, for me, this is the same phenomenon, but without the volcanic pockmarks. I told you we'd be seeing more of these things. Next one, please, Chris. On the subject of fractures, this is one of the most famous faults on the moon's near side. And I think in this image here, you really can appreciate the resolution. But watch what we can see here. The shadows tell us that the straight wall is obviously west-facing. The sun is from the right, the slope is in shadow, and therefore the slope is facing towards the left. But look closely at the straight wall, and you can see that it is not continuous. If you look right there, you'll see that it actually is made up of several slightly offset, overlapping segments. There are actually several more of these segments up there. There's another gap there and another gap there. Now, any of you that have actually looked at the cracks in the plaster at home, you'll know that this is the typical pattern of fracture systems. Discontinuous, slightly offset segments. In the case of the moon, this is a fault formed by the weight of the lavas that fill the Nubium impact basin. That's what this is here. And the center of that basin is to the left of the image. But what's this curvilinear feature here? Just to the west of the crater Bode, which is this one here. Now, it is anchored at either end by two small craters. There's one there, and there's one there. But it's made up of a string of tiny pits. I can certainly see the pits here. I can see them there. They've actually coalesced together. But it's made up of a string of tiny pits, rather like a string of pearls. It's not straight, but it too is discontinuous, just like the straight wall. And there is the discontinuity. There's the gap and the step over and the slight overlap. This looks to me like a curved version of the alignment of pockmarks we saw north of Archimedes. In other words, a fracture-controlled volcanic feature. I'll explain why I think it's a collapse feature in the next slide. Next one, please, Chris. Oh, good. I really hope that this one would be illuminated properly. Here on the east side of the Mare Humorum, down here, is what I think is one of the most extraordinary images in this entire Japanese Space Agency set. The lavas that filled the Mare and flooded or nearly drowned the ancient crater Hippalus, which is what this thing here is, they are themselves cut by three superbly resolved parallel rift valleys. Here's the first, there's the second, and here is the third. Now, as rifts go, these are long, skinny, and shallow. But they also vary in character along their length, and in fact the central one seems to fade out in its midsection. I can trace it easily to here, and then it seems to disappear. Then I can pick it up again, and away we go, and right the way down to here with no problem. Now, in fact, if you also look very carefully at that central one, you'll see that it's made of at least 2 segments which are staggered. I can come up, let's see if I can spot this one here. Yes, there we go. I come on up through here, and it stops. I've got to step over and keep on going. And in fact, the 2 segments overlap very slightly. Just like the feature we saw in the straight wall. Skinny, shallow, staggered rifts like these on Venus and Mars have been interpreted by planetary geologists as fractures which guided the rise of narrow sheets of lava, molten rock, from deep down. What geologists call dikes. Lava that got close to but didn't actually quite reach the surface. When the lava cooled and crystallized, it shrank, leaving a gap just beneath the surface into which the surface rocks dropped, rather like a keystone. And that created the appearance of these very shallow, skinny rift valleys. Now, there seem to be as many impact craters affecting these rifts. You can see those ones there, obviously, but there are also lots of small ones in the rifts themselves. And that tells us that these dike-related rifts are also ancient. Next one, please, Chris. Now, let's go to Schroeder's Valley, which is up here on near the northwestern limb. Many amateur astronomers are very familiar with this valley. It's quite an amazing valley. It's well imaged here, and good, it's well illuminated too, as an eroded squiggly valley. That's this thing here. See, it's squiggled as it goes down there. And it was carved by basalt lava flowing from the high ground. That's what this is here. This is actually high ground here. Flowing from the high ground adjacent to the craters Herodotus and Aristarchus, that's Herodotus and Aristarchus, down to the floor of Oceanus Procellarum. That's this out here. Now, that's nice, but what I want you to focus on here is actually in the foreground of this image. I want you to focus on this feature, and then eventually this one here. Oh, you can also focus on that one there too, if you like. Those features in the foreground, they are multiple wiggly alignments of small pits. I think you can clearly see the pit structure in this one here very easily. Here's a series of slightly larger pits on this one. That one actually is also made of pits. Now let's zoom in and let's change angle. Next one, there we go, Chris. Excellent. So several of these squiggly alignments are clearly made up of chains of small pits. You can really see it there. I think there's no doubt about it. This one here is also made up of small pits.
They look like reels.
They look like
reels, but they're not reels.
They are rills, but how do rills form? That's what we're coming to. Now, these things, I say, the pits are identical to each other like peas in a pod, or like pearls on a necklace, if you will. Now look at the right part of the image, this thing here. And you can see a similarly squiggly valley, except this one is clearly a skinny rift, whose northern part, because we're looking south, the northern part here, if you look carefully there, it actually has a serrated wall. The wall is not straight. This looks like a fracture-controlled volcanic collapse pits that progressively coalesced with one another to form a collapsed rift at the top of a series of squiggly dikes. In other words, a variation on the theme of the dike-related rifts that we just looked at in the Mare Humorum. Next one, please, Chris. We're going to skip this one. At the end of the Kaguya mission, yes, we're going to skip that one. JAXA, the Japanese Space Agency, had determined that it would crash the satellite into the moon's surface near the South Pole, just here, but on the far side. I got to admit, I still don't actually understand why they did this. I'm not sure what they were actually trying to do. Whatever, the close approach of the satellite gave us unprecedented high-resolution images of the lunar surface as it came into crash. Here, I think, in this image here, compared with the dark image of Mons Pico, I'm afraid, but here I think you can really appreciate the dusty texture of the lunar surface. Again, the result of billions of years of gardening by micrometeorite bombardment. I had never seen anything that really brought home the message of dusty lunar surfaces like these before. This dusty lunar soil is technically referred to as regolith, in case you come across that in your reading, and it's peppered with small impact sites. You can see the craters everywhere. That means it's not that young. The next image will be zeroing in on this box. So here we are, as we drop even closer to the surface, the dusty nature of the surface is now even more apparent. And you can see now a large number of small pockmarks all over the place. You see them down there? And then through here you see these pockmarks. Well, they're all over the place. They're everywhere. And again, the next image, we'll be zeroing in on this box, and we'll zero in on that peak there. The foreground here, quite frankly, that looks, if I showed you this and didn't tell you where it was from, that foreground looks like a sand dune. But in fact, it's rock coated with a thick, uniform layer of dust. Go again, Chris. One final box, and we're going to zero into that box there, into that crater. Just before the crash, dust is clearly the dominant feature in this image. But again, look carefully. And you can see that impact-related pockmarks in the dust down here. I don't mean these big things here. I mean these little pockmarks out here. Those pockmarks are partially covered by dust associated with the large impact crater, this one here, that dominates the image and is itself impact-free. In short, the large crater is younger than the pockmarks. And this indicates that the meteor that formed the big crater impacted an already thoroughly gardened, dusty lunar surface with a regolith that was at least as thick as the crater's cavity is deep. I don't know exactly what that depth is, but that's clearly a minimum of tens and tens of meters. Final slide, please, Chris. Now, as I stated at the beginning of the talk, many of the features illustrated by these high-resolution images will not be apparent even through powerful amateur telescopes, though many will be. Nonetheless, I think that they're going to stimulate many amateur astronomers to see the moon through different eyes as they observe. So remember, the next time that you observe the moon through a telescope, remember the following three things. First, the rocks you're looking at are likely covered by a thick, uniform layer of dust. You would not want to be standing there, nor would you want your telescopic equipment there either. Secondly, there's more to the lunar surface than impact craters. Keep an eye out for arrays of parallel fracture systems, and don't be surprised if you see two of them, two different sets of fractures at different angles in the same place. This is actually standard for fracture systems. And thirdly, in some cases, these fracture systems appear to control volcanic processes, ancient volcanic processes, especially the emplacement of vertical sheets of lava, or dikes, and the collapse structures above them, which can even lead to the formation of skinny and observable by amateur telescopes, skinny rift valleys. If you want to see more of these images in high definition, go to the Japanese Space Agency website. The images there are amazing. What I've done here, I've pulled them off, I've degraded them, obviously, get them into PowerPoint, so my PowerPoint isn't too big for the computer. But they are amazing when you actually pull them down yourself. And if you're hooked on TV, hooked on high definition TV, then go to the Japanese Space Agency channel on YouTube, where you can actually follow short high definition movies that will make you feel as though you're really orbiting the moon yourself. Thanks for listening.
Good, that does it for our program for tonight. Just a few announcements before we pack it in. First of all, a reminder for you, what we announced last time around, the change in policy regarding astronauts. Astronauts up to now has been free in either the PDF or the print or mail version. As of the point that you renew your membership, you'll have an opportunity to select whether you wish to pay $15 a year to have the print copy, or for free you can continue taking the PDF copy. So that will take effect whenever your individual membership comes up for renewal this year. Next, we've been contacted by the International Astronomical Youth Camp, which this year is being conducted in Germany, Klingenthal in Germany. It's
It's a 3-week stint from the August 1st to August 21st. It's open to youth up to, I seem to remember it was up to age 24, something like that. So if you have some younger people who might be interested in this, please take a look at their website. It's www.iayc.org. I've gone and looked. It's quite interesting to take a look at, and you might want to ship your young'uns over there and get yourself some peace and quiet for a few months. Alrighty. Upcoming this month is Earth Hour. For those of you not familiar with it, I suspect many of you are. It's an opportunity for people to turn off their lights for an hour. It's not directly something that I guess astronomers do. It's not driven by astronomers. It's more, the ecology crowd, that sort of thing. But it's also an interesting opportunity for us to join together with others and just see how much difference it makes to turn off those unnecessary lights outdoors. So the hope is that more people will participate this year. Again, it's on March 27th, 8:30 p.m. Turn your lights out for an hour and see whether the sky gets a little darker. Next up. Again, we have a few more of the calendars left. When I last checked, I think there were 2 or 3 left in the box. So if there's a couple more people want to take them off the Society's hands, I'm sure it's much more beneficial for us to have dollars than calendars. So that'd be great. This evening, afterward, will the libraries be open? Estelle? Okay. So I suspect the book library will be open. Estelle will be there running it. The equipment library, I know Elle's here, so I imagine it's open as well. Coffee and Conversation with Art and Ann Fraser out front. Membership info also with Art. And just a note, you might have put 2 and 2 together and gone, wait a second, if there's no paper astronauts, how do I get my membership card? Because it's always taped inside. You'll go see Art Fraser about that, and he'll give it to you in person once you've renewed. Please remember, the rest of the museum is closed, so stay between here and the doors, I guess, would be a good idea. The usual reservation at Kelsey's. Anyone who wants to go join the group over there is welcome to do so. This evening's attendance was 144 souls. I think considerably augmented by children tonight. I saw a lot of youngsters around. Well done. Okay, many thanks to all of the contributors to tonight's meeting and to our host, the Canadian Science and Technology Museum. Any bitches, any observations of any sort, any ideas for presentations, please get hold of me. My email address, not too difficult, bill.wagstaff@rogers.com. Next meeting is not the first Friday of the month. Please don't make the mistake I've done several times and come the wrong week. It's on April 9th. We've moved it to make way for the Easter holiday, right? Don't want to run up against the Easter long weekend. Anyway, hope you've all enjoyed tonight's program, and we'll see you in 5 weeks. Good evening.